This video is, not surprisingly, about Newton's third law. We've already learned about Newton's first and second laws, which basically tell us that force causes changes in motion, or acceleration, and that the acceleration is equal to the net force divided by the mass. What Newton's third law says is that if you have two particles, A and B, and A exerts a force on B, B must exert an equal force on A that points in the opposite direction. Remember that forces arise as an interaction between two objects, and that means that both particles in the interaction experience a force. So drawing a picture, if that's A and that's B, and the force that A exerts on B points in that direction, then the force that B exerts on A has to point in the opposite direction and have equal magnitude. We call these a third law force pair. And when you have two forces that form a third law force pair, they're always the same kind of force, meaning they're both gravity, or they're both tension, or they're both normal forces, and so on. And they're always exerted on two different objects. If you have two forces that act on the same object, they cannot possibly be a force pair because they come from two different interactions. So the classic example of a problem where you use Newton's third law is Atwoods Machine. What Atwoods Machine is a pulley, and from this pulley are hanging two weights, the larger one of mass big M, smaller one of mass little m. The pulley is assumed to be frictionless and massless, and the cord is massless as well. And when we let go of these masses, what's going to happen is that the larger one will accelerate downward, the smaller one will accelerate upward. What we'd like to do is find an expression for the acceleration. Now first off, because they're tied together, the two accelerations are the same. We're assuming here that the string cannot stretch. That would be an interesting problem, though. And when we have a problem like this, we'll draw a free body diagram for each block. The smaller block has a tension force pointing upward on it, and its weight, little m times the gravitational field, pointing downward. The larger block also has a tension force upward, and its weight, big M times g, that points downward. So we'll make that direction, the direction of the acceleration, positive for the small one, and also the direction of the acceleration positive for the larger one. Where Newton's third law comes into this are the two tensions, which are a third law force pair, and are therefore equal. Notice they're not in opposite directions, but that's because there's a pulley there. So if we write down Newton's second law for the smaller block, we get the tension, which points upward, minus its weight, equals ma. And if we write Newton's second law for the larger one, in this case the weight is positive, the tension is negative because it points upward, and that equals not little m times a, but big M times a. And now we have two equations, two unknowns. We're trying to get a in terms of little m, big M, and g. We don't want the tension to be in these equations. So what we'll do is we'll add the two equations together. This is something called linear combination. It's a very, very useful technique. So we write the equations under each other like that. They're both true. So if we add what's on the left sides together, and then add what's on the right sides together, we'll get another equation. And notice we've got t and minus t on the left side. So we have big mg minus little mg left. And then on the right side of the equation, we have big ma plus little ma. Solve for A, and we get G times big M minus little m divided by the sum of the masses. And now we're going to check our work. We've got an equation for A. Does this equation make sense? So let's ask about two limiting cases. We'll talk about one limiting case. And that's the one where little m is 0. If little m is 0, what we would expect is that big M would just accelerate downward at g. And if we look at the equation, we have big M minus 0 divided by big M plus 0, and we get A equals G. That's correct. The other limiting case is where the two masses are equal. Work that one out on your own, show that it makes sense there too. There's a whole category of problems that are like this, where you have pulleys and strings and blocks attached to them and so on. Another relatively simple example of this is two blocks with a pulley, small block, little m, big block, capital M. And we want to know the acceleration of the system. For this, we have to introduce the idea of external forces. When it's not just a single particle that's accelerating, but an entire system of multiple particles, what happens is you are concerned with the external forces, and we can rewrite Newton's law as F net external equals the total mass of the system times the acceleration of the system. And so we're going to neglect the internal forces. The internal forces are forces that one part of the system exerts on another part of the system. So in this case, the internal forces would be the tension. Our system is going to be the two blocks and also the string. And so the forces that those two blocks exert on each other are internal forces, and we'll ignore them. We're also going to, because the presence of the pulley is going to make this a little bit interesting on the coordinates, but we'll say that the direction, the positive direction, and the direction of the acceleration is going to be to the left, or pardon me, to the right, and then down. So we'll ask, okay, what forces act on the system? Draw a little picture. We have capital M, we have little m, we have the string between them. Now what forces are acting here? Well, we've got the weight of the large block, big mg, and the normal force on it. And there's going to be a friction force acting on it as well. We'll learn how to calculate that in the next video. And then on the small mass, it's got just the weight acting on it. But its weight points that way because we've kind of straightened it out. It tends to pull the whole system to the right. And we look at this and we can say, well, the acceleration of the system is to the right. And therefore, we know that the normal force and the weight of the large block cancel out, and we can say that the net external force is mg minus F, and Newton's second law says that equals the total mass, m plus big M, times A. And then we can solve for A. We get mg minus F divided by big M plus little m. There we go. Now an example. Let's say you've got three blocks are connected and they are pulled across a frictionless table by a force of magnitude 65 newtons. Blocks have masses of 12 kilograms, 24 kilograms, and 31 kilograms. Calculate the acceleration of the system and the tensions in the connecting cords. So we're going to have a force 65 newtons here. It's a 31 kilogram block. It's tied to a 24 kilogram block, which is then tied to a 12 kilogram block. We want to find the tension here, and the acceleration of the system. It's frictionless, so the only external force on the system is the 65 Newton force. Well, there's normal and weight forces, but we're going to ignore those because they're perpendicular to the direction of motion. And so we can say that the external force, 65 newtons, is equal to the total mass, 31 kilograms, plus 24 kilograms, plus 12 kilograms, all times A. Solve for A, and we get 65 divided by 67, and we get 0.97 meters per second squared for our acceleration. Okay, that was easy. Next, we want to find the tensions. Now T1, we're going to redefine our system. So that our system is now T1, just the 24 kilogram block and the 12 kilogram block. In this case, we notice that T1 in our redefined system is now an external force because the 31 kilogram block is no longer in our system. And so we'll say that T1, that external force, is equal to the total mass times the acceleration of the system, which is 35 newtons. And then similarly for T1, or for T2, we'll redefine our system again so that we just have a 12 kilogram block and T2 is the force acting on it. So T2 equals 12 kilograms times 0.97 meters per second squared, which is 11.6 newtons. Now you'll notice in this problem that the largest force is 65 Newton, followed by T1, and then by T2. The question is, what if we reverse the order? What if we had the 65 Newton force applied to the 12 kilogram block? How would that change what the strongest and the weakest of the three forces are? Little brain teaser for you. Also, tomorrow I'm going to check and see if you have done questions 7 and 9.